Okay, welcome back. I wanted to end our discussion of pKa's by talking about the interconversion of the equilibrium constant for dissociation of an acid and the pKa. And so remember that pKa equals minus the log Ka, okay? And so if I can get to one, I can get to the other. And if I know the equilibrium constant for dissociation of a given acid or two, I can then compare them by comparing their pKa's. And so as an example, consider trifluoroacetic acid. Okay, if I put this into water, this will dissociate to some extent into trifluoroacetate. And H3O plus. Okay. And so I can ask the question, what's the pKa of trifluoroacetic acid? If I know the Ka of the reaction, I can easily solve for that. So the KEQ, which equals the Ka for this reaction, is 0.588. Okay. And we know that the pKa equals minus the log Ka, which is going to be minus the log 0.588, which gets me to 0.23, okay? So the pKa of acetic acid or trifluoroacetic acid is 0.23, all right? We can compare that to our old friend acetic acid. Okay, draw out the usual equilibrium, and I can measure this equilibrium constant, which equals 0.000017378, or we can just say 1.737 times 10 to the minus 5, okay? And so if I apply the minus log function to that, I get a value of 4.76, okay? And so the reason I go through this is to drill home this point that I said before. The lower the pKa value, the stronger a given acid, okay? And by a stronger acid, I mean the acid dissociates more fully in water. Okay, so the equilibrium constant, the Ka, is going to be larger. But because we use pKa's, we talk about the minus log, that flips it, and it means the stronger acids have lower pKa's, okay? And so all of these acid-base reactions that we've discussed are, as I mentioned, under thermodynamic control, and we can relate these to the free energy of the system and the chemical equilibria. So okay, so you recall from general chemistry that the Gibbs free energy is defined as delta G, which equals, let me just quit my messages there. Let's see. Delta G is defined as minus RT natural log of KEQ. And R is the gas constant, which is going to be 1.987 by 10 to the minus 3 kcal, K Kelvin to the minus 1, mole to the minus 1. And the temperature is expressed in Kelvin. Okay. And so we can simplify this equation by lumping together the R and the T for reactions that occur at 25 degrees Celsius, which is about room temperature. So delta G equals minus 1.4 log of KEQ, okay? And so it's useful to have a few sort of delta G values and there's sort of a relationship to KEQ in your head. Small changes in delta G correspond to very large changes in KEQ. And so and this is at 25 degrees C. So you can write out sort of tenfold differences in KEQ. And then the corresponding delta G's. And so okay, so basically every 1.4 kcals in delta G, you shift the KEQ by 10 units, tenfold, okay? And so qualitatively, as my equilibrium shifts to the right, as the products become more favorable, you see that delta G becomes more negative. The system gives off energy. It gets to a lower energy state. And so it's useful to keep this relationship in mind. And so one of the things that we're frequently encountered with is trying to predict the acidity or basicity of species, sort of a priori without, recourse to a table. And we can draw we can sort of outline a couple different trends that are useful in sort of, as you move around the periodic table. And so the first thing is that as you move across a row from left to right, generally, sort of all else equal, you increase the acidity of the species. And so I can think about, for example, our old friend methane, ammonia, water, and then hydrogen fluoride. So I'm going from left to right across the periodic table. And what we find is that the pKa of these decreases sort of faithfully as I go to the right. Okay, so the pKa gets lower. In other words, the species become more acidic. And the way we can rationalize this is that the conjugate base, the corresponding species lacking a proton, becomes more stable. And so if you think about removing a proton from methane, you generate methyl minus. If you remove it from ammonia, NH3, you generate NH2 minus. Water generates hydroxide, HF generates fluoride. In each of those instances, I'm going to a successively more stable anion. The atom that's bearing the negative charge is becoming more electronegative. And so as a consequence, then the corresponding acids become more and more acidic. We can also draw some generalizations about going down columns. And so generally, as you proceed sort of down a column, things tend to become more acidic. So if we consider like hydrogen halides, if we have HF, HCl, HBr, and HI, we see that the pKa's become increasingly negative. So HF is about 3.2. It's actually not a very strong acid, although it is quite toxic. HCl is -6, HBr is -8, and HI is going to be -10. Okay, and so the explanation here is that as you're moving down the column, when you remove the proton from that species, the resulting anion gets larger as you move down the column. So okay, and so if we think about this from the think about the anion as an electron cloud, in HF, because it's a small atom, that negative charge is very localized. Okay, as I go to chlorine, I get a little bit bigger. The negative charge is a little bit more diffuse. As I get to bromide, I get slightly even larger, and then iodide even bigger. Okay, and nature loves to delocalize charge. So anytime that I can spread out a charge, this is a good thing. It is a stabilizing effect. And so as I move down the table and those conjugate bases get bigger and bigger and bigger, the system as a whole gets more stable. So okay. And so the two trends that you want to remember are that as you move from left to right in a given row, things tend to get more acidic. And then as you move from top to bottom in a given column, things also tend to become more acidic. The final two contributors to acidity are probably the most important and the most, sort of common that you'll encounter. And so the first thing is that you have to consider resonance stabilization. Okay. And the general rule of thumb is that delocalization of charge, as I said, when you go down a column, you get a little bit more delocalized. Delocalization via resonance is always stabilizing. So okay. And so if we think about, and so where this factor comes in is when you're comparing sort of identical atoms, but atoms for which different degrees of resonance delocalization are possible. And so a good comparison is methanol versus acetic acid. Okay. And so if I put these in water, there will be some degree of dissociation. Okay. Methanol forms methoxide, and then acetic acid is going to be in equilibrium with acetate. Okay. And so the pK of methanol is about 15. And the pK of acetic acid is about 4.76. Okay. So we know right at the outset that acetic acid is the much stronger acid. The question is why. They both have, the conjugate bases both have a negative charge on oxygen, right? So what's the difference? And the difference is the resonance. So I can draw a resonance structure for acetic acid where I show that that negative charge is delocalized across both oxygen atoms. And so I can push electrons like that. I think we've seen this example earlier in the course. Okay. And so what this tells me is that both of the oxygens in acetate are sharing the negative charge. Anytime you can delocalize charge, that is stabilizing. And so the conjugate base of acetic acid is more stable than the conjugate base of methanol. And therefore, acetic acid is more acidic, okay? The final effect is a little less intuitive maybe, and that relates to what we call inductive effects, all right? And so trifluoroacetic acid has a pKa of about 0.23. Okay. And acetic acid itself, we said, is about 4.76. Okay. And so the trifluoroacetic acid is the stronger acid, has the lower pKa value. The question is why? The only difference between the two is the presence of the fluorine atoms in the trifluoroacetic acid, okay? And we can understand this by remembering that fluorine is the most electronegative atom element in the universe, right? And so if you look at the structures of the conjugate bases, and I'm going to draw them very large here. Okay. They differ in the sense that the trifluoroacetate has those fluorines at the position adjacent to the CO double bond. And because those fluorines are so electronegative, they're sucking electron density away from the carbon, okay? And so we can draw these bond dipoles in there. And there's a big difference in electronegativity between carbon and fluorine, okay? We know that hydrogen is approximately the same electronegativity as carbon. And so there really aren't, you don't have that same type of polarization in acetic acid itself. And so what happens is because you have these fluorines attached to carbon, they're sucking electron density away. What we say is that this carbon becomes partially positively charged. It has an electron deficiency. And so the way we represent that is with delta plus, okay? So okay, and so that partial positive charge stabilizes the O minus, okay? It sort of propagates through the whole molecule. You know, these electrons, and you know, they aren't localized between atoms. They're part of the whole molecule. And if we're literally sitting on one end and tugging electron density with the fluorines, that's going to be felt at even more remote positions, such as this carbon with the CO double bond. And so now I put delta plus next to minus, and that is stabilizing. And so therefore, the trifluoroacetic acid is more acidic. Okay. And so I said to you early on in the course, I said, you know, 3 concepts you need to understand: inductive effects, resonance, and hyperconjugation. So we've covered resonance in sort of a decent level of detail. This is, I think, your first real introduction to inductive effects, and it's going to come up a lot more, okay? But inductive effects are essentially this idea that electrons aren't shared equally between elements of sort of different electronegativity, and that difference in electronegativity leads to bond dipoles, and that in turn contributes to overall sort of molecular dipoles, okay? You're shifting the electron density in the molecule, right? And anytime you can sort of pull electron density away from something that's got a negative charge, that's going to be stabilizing, all right? And so that concludes, I think, all we want to say about acids and bases. Yeah, that ends this lecture. So see you guys on Friday in class.